So last time, someone asked me to remind them what the difference between a lyase and an oxidoreductase was. So really quickly, remind ourselves what those two things are. There were two of the 6 enzyme classes I wanted you to know. An oxidoreductase simply did oxidation and or reduction, right? You can't have one without the other. But you're talking about it gaining or losing electrons, and sometimes hydrogens, protons go along with it. A lyase had a very specific definition. It was you can make or you must make or break a double bond, in other words, single to double or double to single, but you do not do redox. Right? When I say break a double bond, I don't mean double to no bond. I mean a double bond becoming a single bond, or a single bond becoming a double bond. Either one is valid, but you must not do redox when you do that. Okay, so I made this little picture for you to help you see that. Right, and all we're going to do is count. Right, I gave you 2 examples at the top of this thing. On the top left is an oxidoreductase. On the top right is a lyase. And then we'll do an example together at the bottom, which you're going to figure out which one it is. Okay, so what was that? So let's start with, okay, I hear an echo from someone. So let's start with the one on the top left. All right, so we have some molecule here. It doesn't matter what its name is. You could name it if you wanted to. But we're taking it and adding it to H2, right? And then we're going to get this molecule when we're done. The only thing that changed was this double bond was reduced to a single bond. In other words, a pair of hydrogens were added across this double bond. You've done this reaction before. It's hydrogenation. Okay? It's also a form of reduction. Right? So we know this is an oxidoreductase from the start, but let's prove it to ourselves using this little counting technique. Okay? And we'll compare it with the lyase on the right. So of the carbons that are over here on the left, right? So of the carbons that are on the left here, I only want to consider the ones that actually change bonds with something. So I've highlighted those for you. This carbon on the far left, you notice it does not change anything from there to here. It's bonded to the exact same atoms in the exact same way. Nothing changed for this carbon, so I'm not going to count it. It's okay if you do, you're just going to count the same thing twice. Okay, so it won't change your answer, but it's just not necessary to count these that don't change. The carbon on the right, same scenario. It doesn't change at all. These 2 carbons, however, the ones I've highlighted in yellow here, and that I'm circling here, did change bonding partners, right? They definitely are different than they were before, these 2 carbons. So we will consider those. Okay? So I'll write this in there. It might look kind of funky when I'm writing with it, but we'll deal with it. I'm going to ask 2 questions, the before and after picture. How many bonds to hydrogen are being made by these carbons? So the carbons on the left, how many bonds to hydrogen are they making in total? So these 2 right here. I'm ignoring these because they don't change. But how many bonds to hydrogen, I'm not counting hydrogens, I'm counting bonds to hydrogen, do they make? Well, it should be easy to figure out. There's just 2. Okay? So I'm going to ask the question over here afterwards in just a second, the same thing. So we'll just put a 2 here. That looks terrible. Let's try it this way. 2. All right? Same question. How many bonds to hydrogen did those 2 carbons make in the after picture? Well, the answer is 4. Right? So there's 4 bonds to hydrogen over here. So we'll put a 4 here. Right? The next question is, how many bonds to oxygen do these 2 carbons make? Now, these carbons are making lots of bonds to oxygen, but we excluded them from our count because they didn't change. Only the ones that change. So these 2 carbons are making a total of 0 bonds to oxygen. And in the after picture, again, 0 bonds to oxygen. So I'll write that in here. Right? So 0 in both cases. Next thing I want to calculate is the change from before to after. What happened before to after? So when you calculate a change, you take the after minus the before, final minus initial. So the change here was what? I gained 2, so I'm going to call it a plus 2. That should say plus 2. Okay, so I gained 2 bonds to hydrogen. What happened to the bonds to oxygen? Well, I didn't gain or lose any, so the difference was 0. The next question is, are these two numbers the same? If they are not the same, it doesn't matter what they are. If they are not the same, you did oxidoreduction, right? You did a redox reaction. If these two are not the same, and they're not, that is a redox. Okay, everybody get the question? So count the number of bonds to H before, the number of after, the number of bonds to O before, the number after, calculate the difference, or the change, and compare these two numbers. If the changes are the same, it's going to be a lyase. If the changes are not the same, it's an oxidoreductase. Let's do the example on the right and you can see how it works. All right, so these two carbons, again, are the only ones that are changing. This one did not change, and this one did not change. So I'm going to ignore them. I could count them. It would only make all the numbers bigger, and it wouldn't make a difference in the change. But I'll just focus on the ones that do change. So the number of bonds to H here, again, would be 2. So we'll put that in there. The number of bonds to H afterwards, so looking over here, be careful with this one. How many bonds to hydrogen are these carbons making? Right. This hydrogen is not bonded to that carbon. It is bonded to this oxygen. So these two carbons are making how many bonds to hydrogen now? So there's 1, 2, and 3. This one is not bonded to a carbon. So the answer here is 3. So we'll say the after picture is 3. How many bonds to oxygen before? Same as before, 0. And how many bonds to oxygen are these two making now? 1. There's only 1 bond to oxygen over here. So we put those numbers in. Bonds before were 0. The bonds to oxygen after is now 1. Right? The difference between the bonds to H before and after, we had a change of +1. And the number of bonds to oxygen before and after, we had a change of +1. Right? And then we do a comparison. Are these two numbers the same? It doesn't matter what the number is, as long as they're the same, it's a lyase. If they're not the same, oxidoreductase. Right? It's a very simple counting method to figure out the difference in these two. Okay? You guys help me do the bottom one now. We're going to do the exact same thing. First, we need to do some highlighting. So, which of these carbons actually changes bonds? Right? So, this carbon over here, start on the right. This carbon, can you see, is this carbon here? It's the exact same one. Does it change bonding partners at all? No. It looks identical before and after. We can ignore it. How about this carbon? It's bonded to, double bonded to this O, bonded to this carbon, and also bonded to this carbon. Remember, these H's are on this carbon. And that's the same scenario here. It's double bonded to O, it's bonded to this carbon, it's also bonded to this carbon. All 3 of these hydrogens are on this carbon this time. So this central carbon's bonding partners have not changed. I can ignore it. Right? However, this carbon has changed. It's got 2 hydrogens on it. It's bonded to the one on the right and the one on the left. Now it's got 3 hydrogens on it and only bonded to the one on the right. The one on the left has disappeared. It's gone. So this carbon has definitely changed bonding partner. Sorry, this one is that one. They have changed. So we'll consider that one. Right? I'll take and put a little box around those for you so you can remember which ones to worry about. So we definitely could consider that carbon, which is that carbon. Right? We also need to consider this carbon. It was attached to this one before, and now it's freed as CO2. So that one also changed. So we'll put a box around that one as well. Right? So this carbon also changed. And it's over here now. So we don't have to consider those. We'll ignore the other 2, just like in the previous examples. We ignore the ones that don't change. Okay? So now let's ask our questions. Combined, how many bonds do these carbons make to hydrogen? Well, this one's not bonded to any hydrogens. This one's bonded to 2. So combined, their total bonds to hydrogen is 2. So we'll put a 2 there. And then afterwards, how many bonds to hydrogen? This one now has 3, and this one has none. Right? So our total bonds to hydrogen afterwards will be 3. Right? That gives us a change of +1. It's not always going to be +1, just happens to be +1 in this case. Right? Now let's do our bonds to oxygen. How many bonds to oxygen do these two carbons have combined? Make sure you're counting bonds and not number of oxygens. This one has no bonds to oxygen. This one, however, has 3. Right? This is a carboxyl group. Right? It looks just like these up here. This one would have an H on it if I drew it with this H. Right? It looks like that. So it has 3 bonds to oxygen. It has one of these double bonded and the other single bonded. So let's say this one is the one that's a double bond to oxygen, and this one's a single bond. So this has 3 bonds to O. Okay, so we'll put that in our list. So the bonds to O in the beginning, 3. Keep in mind that this one's bonded to 3 bonds to O. This one has no bonds to O. The sum is still 3. In the after picture, this one still has no bonds to oxygen. How many bonds is this carbon making to oxygen? Well, if you remember the structure of CO2, it's a carbon, and each of the oxygens is double bonded to it. So the total number of bonds here is 4. Right? So we'll throw a 4 in our diagram here. Right? That means the difference before to after was +1. Right? So now we do our comparison. Are these two numbers the same? If they are, that means it's a lyase. Right? And they are the same, so we'll take this and label it as a lyase. And that's how you do that. Right? I'm going to put up a few more examples for you guys to try, but this one is probably the most So this one's probably the most difficult because you have to see that the number of bonds on the right is actually 4, right, for the CO2. It's not 2 oxygens. I'm not counting the number of oxygens. I'm counting the number of bonds. Right, so any questions on this before we move on to the rest of the enzyme lecture? You guys can type your question or you can say it, either way. Okay, so I'm going to close this. I'll save that picture for later and put it up on D2L for you so you can see an example. Okay, so I want to go into the remainder of our PowerPoint. It is the new one I uploaded for you. I added a few slides to it to help clear things up. But we're going to start on slide 16, and it looks like this. Okay, and I introduced these last time. I introduced the 2 broad categories of inhibitors. We called them reversible and irreversible. And these names will make sense. The irreversible ones do not come off, whereas reversible ones can bind and then unbind. They can be removed from the enzyme later. Irreversibles, once they're bound, they're never coming off. So the name should make sense. So briefly, let's talk about the irreversibles at the bottom of the slide. These are very simple compared to the top ones. Once they bind, they never come off. What's a great way to do that is to make a covalent bond. They don't have to do that, but it's a great way to do it. Right? So a lot of these are called suicide inhibitors because when they bind, they're consumed. They'll never be able to inhibit another enzyme. They're consumed in that inhibition. Also, the enzyme it's inhibiting will never work again. Right? So this is a permanent turn off with these irreversibles. That's very simple, very easy to understand. Okay? We can use them for things like transition state drugs or affinity labels or things like that. But that's not what I'm interested in you learning today. Those are simple. The more complex one is where the inhibitor can also be removed. That's the reversible ones at the top of the slide. Okay, so the reversible ones at the top of the slide, there are 3 main types. We're going to call them competitive, uncompetitive, and non-competitive. I did not come up with the names. One of them actually makes sense. The other 2 sound like the same thing, and I'm going to try to clear up the difference between the 2. Okay, so we'll talk about the 3, competitive, uncompetitive, and non-competitive next. Okay. There's lots of misconceptions about these, and lots of textbooks oversimplify things, and we'll try not to get into all those soapbox arguments. I just want you to understand the basics. Okay. So let's do competitive first. This one's intuitively simple. Now, you may have heard some things about it that might be true, might not be true, might not always be true. So competitive, all it has to accomplish is when it binds to the enzyme, the substrate cannot. It's a true competition. So if you have an enzyme sitting there and a substrate binds to it, this inhibitor cannot. Okay? If you have an enzyme sitting there and the inhibitor binds to it, then the substrate cannot. One or the other. And that's shown in the little scheme on the top left. If you have an enzyme there and it adds to substrate, it says E plus S forms the ES complex. That means the substrate is bound and the inhibitor cannot bind to that. Alternatively, if the inhibitor binds, you get E plus I in the vertical column, forming EI, and the substrate cannot bind to EI. So it's one or the other. Okay? So a way to say that is our inhibitor only binds to the free enzyme. That's what's labeled as E. The inhibitor, I in this case, will never bind to ES complex if it's a competitive inhibitor. Okay, so following this little scheme, you notice that I, the inhibitor, only binds to E, never to ES. That's all I want you to get out of this slide so far. Okay, don't worry about all the constants. Don't worry about all the constants or the arrows or any other labels, but the competitive inhibitor can only bind to free enzyme, never to ES complex. Okay? Let's talk about the next one, uncompetitive. It's sort of the opposite of that, right? So an uncompetitive inhibitor can only bind if the substrate has already bound. So in the diagram on the left, it says I only binds to ES complex. You notice it never binds to E on the far left, like competitive did over here. Right? I only binds to the ES complex, never to free enzyme. So these two are mutually exclusive events. Either it's competitive or it's uncompetitive. They're opposite things. Hopefully that makes sense. Okay? There is a third option. Okay? And in this option, the inhibitor doesn't really stick to one. It can do either one, right? It probably has a preference for one, or it may not. So in this case, for the non-competitive type, the inhibitor can either bind to free enzyme on the far left, making the EI complex, one more time, or the inhibitor can bind to the ES complex in the center, making the ESI complex. It can do either one of those, obviously not both at the same time, but it can choose to bind if the substrate is absent or already bound. So in some way, you can think of non-competitive as a sum of the first two, right? So we had competitive where it could only bind to free enzyme. We had uncompetitive that can only bind to ES complex. And non-competitive could do either one, right? It probably has a preference for one or the other. It may not. They could be identical affinities. So either any of those conditions are possible. Okay, so knowing those, I want to ask you a couple questions. Okay, so, and I have an analogy for this we're going to talk about later that'll hopefully clear it up. But when we're looking at this scheme, I'll go back to the slide here real quick. Imagine this I stuff is not here. We're just going to look at the first part that says E plus S forms ES, and then ES makes product and releases the product. So we get P released and we get our enzyme back like the beginning, so we can do it again, no worse for wear. It wasn't consumed, it was a catalyst and so forth, right? But what I want you to focus on for this part is E plus S forming ES. There's a little arrow pointing to it. It's got a little K1 written by it. You don't have to know that number at all. But E plus S forming ES. And I ask you, what could happen to ES? One of two things could happen to our ES complex. The simplest thing it can do is just fall apart. E plus S forms ES, right here. E plus S forms ES, and the ES can simply fall apart, let the substrate go. That's represented by the back arrow with that K-1 label. So E plus S falls apart back into enzyme and substrate separately. That's very simple. That's a bind and then a release, and it happens all the time. Alternatively, E plus S forming ES, instead of falling apart, could make product. That's the little arrow to the right, we call it KCAT. Right? So our ES can fall apart two different ways. It can make a product, or it can just let the substrate go. It's like catch and release program with fish. Right? So you can bind the substrate, make a product, or bind the substrate and then release it back to E plus S. What I want you to realize is that the E plus S on that forward arrow forming ES and the ES falling apart back to E plus S is in equilibrium. It's going back and forth all the time. It's bind and release, bind and release, bind and release constantly. So how tightly it binds its substrate is represented by those two relative values, right? If it prefers to bind its substrate, it'll likely go towards ES more often. If it doesn't like this substrate, it'll form E plus S more often. It'll fall apart more readily. Does that make sense? So if you are the right substrate and you have a high affinity for that enzyme, you're going to form ES more likely than you are going to fall apart. If you're not the right substrate, it's very unlikely that you're going to form an ES complex because you just don't bind well. But falling apart would be done very well. If it does bind, it falls apart readily because you're not the right substrate. So it's in equilibrium. Okay? That equilibrium tells me something about its binding affinity. That's what I want you to get out of that. Okay? The other thing I want you to get out of this diagram, ignoring the I for a second, is the ES becoming E plus P. Right? So the ES complex is the only thing in this whole diagram that can actually make a product. So ES, the concentration of ES determines how much product I can make. Right? Under what conditions could I make the most product per unit time? In other words, how can I make it as fast as possible? Well, one thing I can think of is I can throw an infinite amount of substrate at this thing. Make S concentration equal to infinity. That's not realistic, but I can make it really, really high. Right? So we call it saturating amounts of substrate. Effectively, it's an infinite amount. And looking back at that E plus S forming ES, and then ES falling apart to E plus S, if I give it an infinite amount of substrate, am I going to alter that equilibrium? Okay? Think back, this is Le Chatelier's principle. If I add an infinite amount of something on one side, it's going to shift the equilibrium to the other side. Right? I'm going to consume a lot of that product to make the other side, or that molecule to make the other side. So E plus S, S being infinite, is going to make as much ES as there is E. Every enzyme, every E, will have a substrate on it. There will be no leftovers because you have an infinite amount of S around. Right? E is a certain amount, so many of them around. But if every one of them has an S and there's an infinite amount of S left over, all of the E's will have an S on it. So be no free enzyme. Does that make sense to everybody? That gives me the maximum amount of ES that could be possible. Right? And that means that's as fast as this thing could make a product. Right? So if I throw an infinite amount of substrate at it, that's as fast as it can go. That's much like what we said before, where it approaches a maximum speed. That's the V max. That's what we're calling it. Okay? Now let's ask a question about a competitive inhibitor. Does the competitive inhibitor, when I add it, now we're going to not ignore the part of the graph that has the I on it, or part of the scheme that has the I on it, would it change the binding equilibrium? Well, let's analyze it real quick. If I add an inhibitor I, under normal non-saturating conditions, just a certain amount of S laying around, not infinite, the enzyme will have to choose. It'll bind to S or it'll bind to I. Some of it will bind to inhibitor and form that EI complex. So isn't it effectively removing some of the E from that equilibrium reaction we talked about? The E plus S forming ES and ES falling apart? As I add the inhibitor, I'm removing something from the left-hand side. And Le Chatelier says if you remove something from one side, the other side will go that way to compensate. So if I start removing some E from the left-hand side by involving it in a reaction with I, some ES is going to fall apart to make more E plus S. It's going to try to restore equilibrium. But overall, what that looks like is E and S are spending less time together. More of them are falling apart in the presence of this inhibitor. So a competitive inhibitor makes it look like E and S don't like each other as much. They appear to have a lower affinity for each other. Okay? Let's do that same analysis for uncompetitive. Here we have E and S binding to form ES again. ES can fall apart to E plus S one more time. Under these conditions, with an uncompetitive inhibitor, it's actually involving the ES complex in another reaction. It's removing the right-hand side this time. So what's going to happen to compensate? Again, lyase says the left-hand side is going to form some ES to compensate for the one I'm removing. So it's going to shift that binding equilibrium towards the ES complex, or towards the bound state. So in the presence of an uncompetitive inhibitor, it appears to us that E and S are spending more time together. They must have an apparent higher affinity for each other. That's the opposite of competitive. And lastly, with non-competitive, the inhibitor is removing things from both sides of the equilibrium. So will it shift left or right? Well, if it's removing them both equally, it won't shift at all. So the apparent affinity would remain the same. But it's not always true that it binds with equal affinity to each one. I might prefer binding to E, or I might prefer binding to ES, and most likely it has a preference. Those are separate molecules. And so it could cause the affinity to shift either direction. That'll be part of our story in the analogy I can tell you in a little while. Okay? So to review those real quick, if I add a competitive inhibitor, and it's not best to just memorize these. If you can walk through the algorithm, you'll never have to memorize this stuff. Right? So if I add a competitive inhibitor, it removes something from the left-hand side, so the right has to shift left to compensate. So it looks like E and S are falling apart, spending less time together than they normally would without this inhibitor around. So their apparent affinity has gone down. Right? And a lower.
Dr. May,
Yeah?
do we need to understand the graph on the right?
We'll get to the graphs in a second. I want to get you.
Okay.
Yes,
my
you will,
bad.
but that's a good question. We'll get the schemes down first, and then I'll explain it in the graph, and I can sum it all up in 2 sentences for you. You'll see.
Okay, cool.
But I got to get you there. So, if you have a competitive inhibitor around, and it binds to the E on the left, removing some of it from the equilibrium, ES is going to fall apart a little more than it normally would to compensate, to restore equilibrium. That's Lyase principle. So with a competitive inhibitor, it appears they have a weaker affinity. The true affinity hasn't changed, but it appears to be weaker. I'm adjusting it. I'm having an effect. Right? For an uncompetitive inhibitor, I'm removing something from the right-hand side of the equilibrium. So it appears that they spend more time together to replace those. Here, the inhibitor has the effect of making it look like they have a higher affinity. The true affinity hasn't changed, but it looks like they like each other more. And this one could go either direction or could stay the same. Just depends on what I prefers to do. Okay, so in the first one, let's review that one more time and add one more statement to it. In the first one, the inhibitor, bound on the left, shifts the equilibrium left towards the unbound state. They appear to not like each other as much. So a lower apparent affinity, which means a higher Km apparent. Remember, Km is reciprocal to that. We talked about that last time. Right? A high Km means very low affinity. A low Km means tightly binding, high affinity. So in this case, the competitive inhibitor is shifting it left, making it look like it's binding more weakly, not as tight binding, falling apart better, however you want to say it. But that means we have an apparent higher Km, an apparent lower affinity. Okay? For this one, for the uncompetitive, it shifts it to the right. It looks like they're spending more time together to compensate for the missing ES. So they have an apparent higher affinity for each other or an apparent lower Km. And in the last one, it could go either way, depending on if the inhibitor prefers to bind to E or prefers to bind to ES. So it could go either way. Very rarely will it be exactly the same, where they have equal affinity. It's possible, but it's not very common. Okay? Okay, so I summarized that in this slide, right? And I want you to just memorize these, because it doesn't help. If you try to memorize a list and you make one mistake, you're going to mess them all up. It's easier to learn the algorithm of let's derive how it happens. Okay, so I just summarized it here for you, but I'd rather you be able to walk through those 3 algorithms of which way does it shift it, what does the apparent affinity appear to do, how does that affect the apparent Km. If you can walk through those, you'll arrive at this slide. Right? You don't have to memorize this slide. Okay? So lastly, let's talk about the Vmax for each of these conditions. We did Km, and let's do Vmax. And I'm going to state this over and over and over. It's the same way that I learned how to do it. It's Vmax occurs under what conditions? Well, the conditions for Vmax are when you have as much ES as possible. How do I get as much ES as possible? I throw an infinite amount of substrate at it. Okay, so I throw an infinite amount of substrate. Will there be any free enzyme left over? No. All of it will be bound to S. That's how I got all of it in the ES form. Can the competitive inhibitor do anything under those conditions? It only binds to E. It never binds ES. So in the conditions of saturating amounts of substrate, infinite S, there is nothing for the inhibitor to do. It just has nothing to bind to. So the competitive inhibitor has absolutely no effect on Vmax. Another way to state that is, the name kind of makes sense here, competitive. If you compete with infinity, you lose every time. So a certain amount of inhibitor is trying to compete with an infinite amount of S to bind to E. You can't compete with infinity. You will lose every time. So under those conditions, the inhibitor has nothing to do, the competitive inhibitor has nothing to do, there's nothing to bind to, nothing available, so the Vmax remains unaffected. For both uncompetitive and non-competitive, the inhibitor binds to the ES complex in both of these cases, correct? Right? So under Vmax conditions, again, we'll ask ourselves, how do I get to Vmax? I have as much ES as possible. How do I get as much ES as possible? I add saturating amounts or infinite amounts of substrate. Well, there'll be plenty of ES around in that case. That's what we just said. So can the inhibitor, be it uncompetitive or non-competitive, still bind? Absolutely. That's what it binds to. Right? So will the Vmax be affected? Yes. So in both of these cases, uncompetitive and non-competitive, the Vmax will appear to be less because not as much ES is around as it could be. Because some of it's tied up as ESI. Okay? Whereas in the competitive case, you can't make ESI. So the Vmax remains unaffected completely. And that's summed up in this slide as well. I listed what they do to the KMs and what they do to the Vmax. Okay, so I don't want you to memorize this slide. I mean, it's okay if you learn, if you do, but I'd rather you know how to arrive at those answers, because working through the logic makes much more sense than just memorizing numbers you don't know why they are. Okay. So here's the same thing on the right, the same three schemes on the right I put on one slide for you. Ignore the graphs on the left for now. We're going to tie those in just a minute, but I want you to rehearse what you did on the right. So for competitive inhibitors, that's the one at the top right, you can ignore the values and the KIs, and we're not going to cover those in this class. But the scheme I want you to know. So for competitive inhibitors, the inhibitor only binds to free enzyme. It forms an EI complex. It never binds to ES. For uncompetitive inhibitors, it can only bind to ES, forming the ESI complex. It never binds to free enzyme. Non-competitive is the sum of those two. It can bind to either one. Okay, that's the schemes on the right. Okay. Now let's look at the graphs, and I'll try to tie the graphs together for you. Right? And maybe you should make this list on your own too. Think about it, write it down on a piece of paper in your mind or wherever. It's a very short list. On the graphs on the left, I'm drawing a bunch of straight lines. And think back to high school. How many numbers does it take to describe a straight line? Right? If you remember the equation, it was y equals mx plus b. Right? The x and the y were the variables, right? The axes, right? But it had some constants in that equation, m and b, right? Y equals mx plus b. The m and b were constants. M represented the slope, and b represented the y-intercept. So if I give you an m and a b, it completely describes the line. That's all I need to know to draw the line. Give me the slope, give me the intercept, I can draw the line. I know where it crosses the y-axis, that's the intercept, and I know how high to make it rise with a certain amount of run on the x, that's the slope. Once I draw 2 points, I have the line. Okay, so there's a bunch of lines on those graphs on the left, and let's focus on the top one first, competitive. There's 4 different lines drawn there. What can you tell me about their m's and b's, their slopes and intercepts? So for the first one, competitive, all those lines seem to go through the same y-intercept. Everybody can see that? It all crosses the y-axis at the same point. But they in no way have the same slopes, right? The slope is varying with every one of those, right? So for competitive inhibitors, the intercept of all the lines is the same, but the slope is definitely changing. Okay, let's analyze the second one. In the second graph, we have 4 lines again. They definitely don't have the same y-intercept. The y-intercept is different for every one of them, right? Where they cross the y-axis is different. But they're all parallel lines. And parallel lines, by definition, have the same slope, right? They don't cross the y-axis at the same point, but their rise over run is the same. Their slope is the same. Okay, so for uncompetitive inhibitors, they have the same slope, but a different y-intercept. And in the last one at the bottom, what can you tell me about those 4 lines? Well, they all have different slopes again, and they all have different y-intercepts. The lines do cross, but they don't cross on the y-axis, right? So in a non-competitive case, they have a changing slope and a changing y-intercept. Now, a lot of books will call this mixed inhibition, with non-competitive being a special case of it. But under these definitions, we're going to call all of those non-competitive. Okay, so in the first case at the top, let's briefly remind ourselves what these 3 look like. Competitive has a changing slope, constant y-intercept. Uncompetitive has a constant slope, changing y-intercept. And non-competitive at the bottom has a changing slope and changing y-intercept. Now, if you think about it, there is a 4th option, right? Let's run down those again. Very briefly, competitive at the top, changing slope, constant intercept. Uncompetitive, changing intercept, constant slope. Non-competitive, both are changing. There is a 4th option, and that's where both don't change, right? Same slope, same intercept. But that would be the exact same line drawn 4 times. There's really no effect, and that's not a real inhibitor. So we can ignore that trivial case. Right? So there's really only 3 cases, where the slope changes and the intercept does not, where the intercept changes and the slope does not, or where they both change. And that's why there's 3 types. The trivial 4th one where nothing changes means it's not an inhibitor. Okay? All right, so I said I can say this in 2 sentences, right, at the top. I want you to focus on the schemes on the right, right? You can ignore the KIIs and KISs for now. Just look at the schemes. What do the competitive and non-competitive schemes have in common? So the first one and the third one, what do they have in common? Well, looking at that, and I want to exclude the middle one, right? So what do competitive and non-competitive have in common that uncompetitive most certainly does not? That would be the ability of the enzyme to bind to E, right? Competitive, I can bind to free enzyme, E, and non-competitive, it can do the same thing. But uncompetitive, it most certainly can't do that, right? We left that out on purpose. So competitive and non-competitive have the ability to bind to free enzyme. Now, translate that into the graphs. What do the competitive and non-competitive graphs have in common that clearly uncompetitive does not? That would be a changing slope, right? The first one and the last one definitely have changing slopes. That's the only thing they have in common. Whereas the middle one, they're parallel. They certainly don't have a changing slope. Okay? Back to the right, let's look at the schemes one more time. What do uncompetitive, the second one, and non-competitive, the third one, have in common? Right? And we're leaving out competitive this time. So what do the second and third ones have in common? Well, that would be the ability of the inhibitor to bind to the ES complex. Competitive can't do that. Right? So non-competitive and uncompetitive both bind to the ES complex. Both can. Right? Whereas competitive cannot do that. So let's translate that into the graphs on the left. What do uncompetitive and non-competitive graphs have in common? Well, what they have in common that excludes the first one is a changing y-intercept, right? Because the competitive one all cross at the same point. Right? So let's state those 2 things again in 2 sentences. So on the right, the ability of the inhibitor to bind to the enzyme, free enzyme, changes the slope on the graph. And the ability of the inhibitor to bind to ES complex changes the intercept. That's 2 sentences. Right? So if the inhibitor can bind to free enzyme, it's going to change the slope. If the inhibitor can bind to ES complex, it will change the y-intercept. Now, if you want to focus on those KISs and KIIs just for a second, I can tell you what those things stand for, and it's really simple. The K stands for constant, because we label everything with the German word constant, so it's K. And then the I stands for inhibitor, the first I. So it's the inhibitory constant. And then there's a letter after that. It either says KIS or KII. And let me let you guess what the S stands for. The KIS is the relationship of inhibitor binding to free enzyme, right? The release of that EI complex. whereas KII is the falling apart of ESI complex, where the inhibitor had bound to ES. The S stands for slope, and the I stands for intercept. So KIS, because that's the one that changes the slope, stands for the inhibitory constant that changes the slope. The KII stands for the inhibitory constant that changes the intercept. Okay, so that's all you have to remember for those. If you can translate the thing on the right, what they do, with how it affects the graph on the left, you've got it. Okay? So I have a little story to help you remember that. And it's my favorite analogy I've ever done. And I usually get some participation from the audience for this. So some of you will have to speak up and answer a question. It's really simple, right? But I want to tell you a story that summarizes that in an analogy, since I like analogies so much. So there's this dog, and Kimberly has named him Watson because he's a very smart dog. He's Sherlock Holmes' sidekick. Right? So there's this dog named Watson who wanted to go to the high school prom. Of course, he was a dog. They didn't let him go. Right? No matter how cute he was or how smart he was, they wouldn't let him go to the prom. So he decides to go anyway. And of course, they don't let him in the gymnasium. So he stands outside and watches the activities through the window. He brought his notebook with him. He's taking notes. He's going to publish this later. And so how this analogy works is we can't see what's going on with the enzymes and the substrates and the inhibitors. They're too small. We can't watch them bind to each other in the reaction. Right? It's just too small and too fast on a human scale for us to see it. Same thing with the dog. The dog doesn't understand human behavior. He doesn't know what dancing is. He doesn't know what the prom is. He doesn't know what affections for one another are. He's a dog, right? But all he sees is when there's this noise happening, he also doesn't understand music. When there's this noise happening, people are dancing with each other. They're together. He doesn't know what dancing is, right? And when the noise stops, they stop dancing. They're apart from each other. So the dog is our point of view. The dog watching human behavior at the prom is our point of view. We are the dog watching enzymes. We can't see what's happening, but we can infer what happens from the effects, right? So the dog doesn't know what's going on in the prom, but he can just judge when they're together and when they're apart, right? When the noise is playing, when the noise is not there. So when you and your date show up to prom, right, you and your date represent the enzyme and the substrate, E and S, right? And we have to make a few assumptions that are true about enzymes and substrates and not necessarily true about humans. So E and S have a certain true affinity for each other that will never change, right? They're molecules. They like each other a certain amount, and that will never change. They're simple molecules. Whereas, humans, you show up with your date at prom, your affinity for each other may change throughout the night. We're going to assume that's not happening here in our analogy. So the true affinity doesn't change. Right? And then we need some inhibitors. Inhibitors are your classmates that maybe you didn't like so much, or class clowns or something. And I'm going to get some names from the audience in a second. So the dog is our point of view on enzyme kinetics. He's seeing human behavior like we see enzymes. We can only observe the outward effects. We can't see and understand what's going on because it's too small. Okay? So I need a name from someone that you may not have liked in prom or during your prom or high school career. Hopefully not in this class. Right, so someone give me a name. Doesn't matter what the name is.
Bruce.
Bruce, okay. So Bruce is going to be our first inhibitor. Okay, so while you and your date are the enzyme and substrate, who's which doesn't matter, but you and your date are dancing and not dancing, or dancing and not dancing. Can you see that relates to the E plus S forming ES, and then ES falling apart to E plus S, and that's the equilibrium. And the dog's making note of how long you dance, how long you don't dance, right? And then Bruce shows up. And Bruce likes to dance with your date, right? So while you're off getting drinks, right, you come back and the music started, but you can't dance with your date because Bruce is dancing with your date, right? And you're not going to cut in or anything like that because enzymes and inhibitors and substrates don't do that, right? So you just wait, and then when they're done dancing, you can dance with your date again. But from the dog's point of view, you are dancing less often with your date because Bruce is there, right? He doesn't understand the whole interaction of not cutting in and all that. He's just a dog. But from his timing of measurements, you danced with your date less when Bruce was present. What type of inhibitor is Bruce?
Competitive.
Competitive, exactly. right? Does that make sense? If Bruce is dancing with your date, if I is bound to E, you can't. Substrate cannot bind to E. Right? So it's perfectly valid. That's an easy one to see. It's competitive. It's true competition. Right? All right, I need another name. Someone who is kind of a class clown. Hopefully not in this class.
Sammy.
You said Sammy?
Yes.
Okay, so Bruce was our competitive inhibitor. Sammy this time is going to be a little different. Sammy doesn't like to dance with people. Sammy, I don't know if it's a male or female, it doesn't really matter, but I'm going to give it a pronoun in a second. Sammy only likes to dance with couples who are already dancing. Right? So Sammy comes along and bear hugs couples dancing. That's all Sammy does. Right? Doesn't ever dance with anyone by themselves, but Sammy likes to bear hug couples dancing. That's it. Right? So the music starts again, you're dancing with your date, and along comes Sammy and gives you a big bear hug. Right? When the music stops, from the dog's point of view, when the noise stops, you should separate from your date. But you can't because Sammy's got you in a bear hug, right? Both of you. So from the dog's point of view, you seem to be spending more time with your date dancing than you were before Sammy showed up because you can't separate. Sammy's just telling you jokes or something. He's just hovering over you, bear hug, can't let you go, right? What type of inhibitor is Sammy? Which one does that appear to be on the right?
Competitive?
Competitive? Is that what you said?
No, uncompetitive.
Uncompetitive, correct. So Sammy only binds to couples already dancing, right? Only binds to ES complexes, never to individuals like E alone. Okay? So Sammy would be an uncompetitive inhibitor. Right? And lastly, I need one more name. I need one more name from the crowd. Doesn't matter what it is. Not the first two names, though.
Chris.
Chris. Okay, so Chris likes the options. Chris will dance with your date while you're off getting drinks or going to the restroom or whatever. But Chris will also bear hug couples dancing. Right? So clearly this is going to be the non-competitive case. But Chris likely has a preference for doing one or the other. Right? It's very unlikely Chris does equal with equal time, does both with equal time. Right? So like most real inhibitors that are non-competitive, it prefers to do one over the other. Right? So it could look like you're spending more time with your date if Chris prefers the bear hugging method, or if Chris actually prefers the dancing while you're off getting drinks over bear hugging, it could look like you're spending less time with your date. Right? So it could look like either way to the dog. Okay? Is this making sense? The competitive one, which was Bruce, makes it look like you're spending less time with your date. Bruce was a competitive inhibitor. It looks like you have a apparent lower affinity for your date. Your true affinity, like we said, has not changed. But from the dog's point of view, it looks like you're spending less time with your date. So he writes down that you have an apparent lower affinity or an apparent higher KM. Right? In the second case, what was the name? That was Sammy. So in the second case with Sammy, it appears to the dog that you're spending more time with your date, right? So he writes down that you have an apparent higher affinity, which means an apparent lower Km, right? And in the last case, he could go either way with that, or he could say it hasn't changed, depending on what I forgot what the name was, the last one, Chris. So if Chris prefers bear hugging or Chris prefers dancing with your date, you can go either way, okay? Right, this analogy help make sense for these three?
Mm-hmm.
All right, there's one more. There's one more that I need to add to the end. We need to go back to the irreversible enzymes. Remember those? The ones that bind and never come off? Okay, so I have that part of the analogy too. So the dog, he's got all this information down. He's going to publish this on YouTube or a paper. He's going to get some credit for it because it's a dog publishing a paper. So he also thought he needs to include the other part, the irreversible enzymes as well. So he's kind of still upset he didn't get to go to prom. So he pulls out his cell phone. Yes, the dog has a cell phone. So he pulls out the cell phone and calls the police, right? Because he's a smart dog and these kids are under 21 and you remember the drinks, right? So he called the police show up and they start arresting everybody, right? And when they do, they put you generally in handcuffs, right? So the dog's point of view now, everybody who gets put in handcuffs is never dancing again, right? No matter if the music's playing or not, there's no dancing going on, right? And those generally don't come off, right? From the dog's point of view, they're irreversibly bound. So the handcuffs represent an irreversible inhibitor, right? You're not dancing again. Will those handcuffs ever come off? From the dog's point of view, no, you left with them. And they'll never inhibit someone else dancing. That one particular pair of cuffs will only inhibit that person and no one else. It's irreversible. We call them suicide inhibitors. They're used up in the inhibition. Okay, so hopefully that little analogy makes sense on helping you remember which way things go. Okay, switching gears a little bit, I want to finish the slide set with just a couple slides. How we regulate enzyme activity. All right, we already talked about how temperature can do it, and how pH can do it, and how substrate concentration can do it. That was on the last lecture. But we can also modify the enzymes by adding something else. And I don't mean a substrate, and I don't mean an inhibitor necessarily. I mean we modify the enzyme somehow, right? We could have a molecule, it may or may not be an inhibitor, bind somewhere else on the enzyme, right? That's called an allosteric site. Allosteric literally means other place. So somewhere else other than the active site, something binds. And when it binds, it may make the enzyme work better. We call that a positive regulator. Or it may make it work not so well. That's a negative regulator. Right? So another name for a positive regulator is an activator. And another name for a negative regulator is an inhibitor. But if it's an allosteric one, it binds somewhere other than the active site. Right? If it binds in the active site or not, doesn't tell me which of these it is at all. That's a misconception they put across in books all the time, where they equate competitive with active site and others with not being an active site. And that's not necessarily true. Okay? These three can have binding anywhere on the enzyme. All they have to do is accomplish their goal. Competitive would prevent the substrate from binding. Uncompetitive will only bind if the substrate's already there. And non-competitive doesn't care, it can do either one. Where they bind is irrelevant. In this case, allosteric specifically says it binds somewhere else. That's what the word means. Okay? It's not equivalent to non-competitive at all. That's an oversimplification. Right? It's leaving out other possibilities. Right? Right. And another example of that is how we describe the inhibition or the regulation. So in this case, on the figure on the left, we call it negative feedback. You've probably seen this before, but let's talk about this pathway real quick. We have a molecule in green here, A, and it's converted by enzyme number 1 to molecule B in blue. Enzyme number 2 converts molecule B to C, and then enzyme 3 converts C to the red D. Okay? And if I let this reaction take place, I keep supplying it with lots of A, it'll get converted to B to C to D, right? And D will build up in concentration, right? Until enough D builds up that it inhibits enzyme 1. So D is one of those negative regulators of enzyme 1. It's called negative feedback. And what will happen? Well, D will turn off or turn down enzyme 1, which will convert less A to B, making less B available for enzyme 2 to make C, making less C available for 3 to make more D. So the concentration of D will level off, right? And if it gets too low, if D starts becoming scarce, then enzyme 1 will not be inhibited as much, and it'll make more B, and make more C, and make more D. So ultimately, this will stabilize at a steady concentration of D. This is called homeostasis. This is how most of your molecules and enzymes in your body work, right? There's a pathway where the end result of the pathway usually blocks the first step in the pathway. So you end up with a constant concentration of D no matter how much A you throw at it. Okay? Alternatively, on the right is positive feedback. What this does is we have a molecule W turning into X, turning into Y, turning into Z by these enzymes 4, 5, and 6. We just number them differently so you don't get confused. They have nothing to do with the ones on the left. In this case, enzyme 5 converts X to Y, and then Y is converted to Z by enzyme 6. If Z builds up, it actually goes back and binds to enzyme 5 and says, work faster, work better, do it better on enzyme 5. This is not feedback at all, or not negative feedback at all. It's this amplification. This is positive feedback. So this is like taking the microphone and standing in front of the speaker, right? You know that nasty, loud feedback you get. right? This is what this is on a molecular scale. So what will happen in this case? X will be converted to Y gets converted to Z builds up in concentration and tells enzyme 5, make X into Y faster, which will of course build up even more Z and tell enzyme 5 to go even faster. And you see this is an endless spiral. What will eventually happen is you'll consume all of W gets turned into X, and all of X will get turned into ultimately Z. We will exhaust our supply of W, right? And then this thing will stop. On the left, no matter how much A I threw at it, I ended up with a steady concentration of D. But on the right, no matter how much W I throw at this thing, it will consume it all. Right? Turn it all into Z, right? Examples of this are, there's many, many examples on the left of how most molecules are done. I wrote tryptophan synthesis. So if your body's making the amino acid tryptophan, right, or if you're a bacterium making tryptophan, you'll stop making it when you acquire a certain concentration. That's what this is telling it to do. Don't waste raw materials on something you have enough of. Whereas on the right, this is like oxytocin production. So during childbirth, you produce oxytocin, which causes dilation, and the dilation signal is more release of oxytocin, which causes more dilation, which causes more release of oxytocin. You get the idea. It's an endless loop until you've consumed all the oxytocin, right? Until you've consumed all the, not the oxytocin, but the precursors for oxytocin in those cells. Does that make sense on these two? There's negative feedback and positive feedback. In both cases, a downstream product either inhibits or activates an enzyme further up in the pathway. Okay? And lastly, we can modify an enzyme by putting groups on it, covalently modifying it, like making a covalent bond to something. Look at the very bottom of the slide real quick, and you'll see 3 amino acids I drew down there for you. Right, your 3 alcohol amino acids, so threonine, serine, and tyrosine. And to each of them, on their R chains, they had an OH. That OH has now been replaced with a phosphate. Right, so a phosphate's been attached to the oxygen. So you see on the left, the threonine, the R group's at the very bottom. Instead of having an OH there, is an O phosphate, OPO3. Same thing in the middle with serine, and same thing on the right with tyrosine. Right, the OH on the ring is now an OPO3. And so there are enzymes that do this. They take the phosphate from a donor, usually ATP or GTP or something like that, and they attach it to the enzyme. Okay, the example on the left is we have an enzyme called glycogen phosphorylase. It's in red. And some other enzyme, phosphorylase kinase, adds a phosphate to it. Don't worry about the phosphorylase kinase being green or with a P on it. Just look at the middle reaction. Glycogen phosphorylase, red being off, doesn't work very well. When I put the phosphate on it, it now works very well, right? And it degrades glycogen. That's its job. You don't have to remember this specific example. Just know that when I add a phosphate, it could activate an enzyme. On the right, I have an enzyme that's normally active, glycogen synthase. This time when I throw the phosphate on it, on one of its amino acids that you see down below, then it turns it off, which is exactly the opposite. So in some cases, when you phosphorylate an enzyme, it makes it on or better. And in some cases, like the one on the right, when you phosphorylate it, it turns it off or slows it down. Both are entirely possible. Okay. Right. So any questions on the first thing we did, which was telling the difference between oxidoreductase and lyase, or going over the different types of reversible inhibitors, if the analogy makes sense, because there's parts of it that don't quite mesh with you, be able to tell the 3 types from their schemes with their graphs, or anything on the allosteric inhibition we did at the end.